Welcome to this lecture. This is in module 2 and this lecture is on effective current model for NTV combinational gates. So, today we will discuss the effective current of near threshold voltage combinational logic gates, especially NAND gates. The same would be valid for NOR gates, a similar approach, and we will also discuss the, as a part of this we will also discuss the charging and discharging mechanisms of NTV combinational gates. So, in the previous lecture we have discussed the effective current model of a near threshold voltage inverter, and the effective current model we had obtained to be this, and then we said that from the effective current model we can get the logical effort of an inverter with respect to a template inverter in the near threshold voltage regime. So, we will continue this approach for a 2 input NAND gate and then we will comprehensively discuss the logical effort. So, when we discuss near threshold voltage regime, the upper transistor and lower transistor switching in a NAND gate, upper and lower transistor switching would have a very different performance regarding the output delay. The reason we will discuss. First thing is, in combinational logic gates we would not be discussing a series stack larger than 3 transistors. The reason is that in near threshold voltages you can observe that whenever there is a discharge happening, for example through this series stack a discharge is happening for the output capacitance, the gate voltage of the upper transistor is Vb minus Vx. Vx would have a certain value and therefore, it would be a smaller value, isn't it, than VDD always. It can never be VDD while discharging. So, it would always be smaller. VDD itself is near threshold voltage. So, this is much smaller. VGS of M2 would always be smaller than the threshold voltage. So, if we increase the stack height, for example, if we have a 3 input NAND gate. So, I am just drawing the pull down network of the NAND gate, 3 input NAND gate. A, B and C inputs. Suppose the input C switches high, okay, and these are at VDD already. So, what would happen? For a current to flow through these 3, there would have to be a certain potential which develops across Vx1 and Vx2, and Vx2 would be larger than Vx1. So, therefore, Vgs of C would be smaller than Vgs of B, and this would be smaller than VDD, as we can see, because there has to be a certain VDS, a drain to source voltage for transistor A for this to conduct, for there to be a discharging current available. Likewise, there has to be a certain VDS for VB for the transistor B for it to conduct, isn't it? So, therefore, Vx2 would be larger than Vx1. So, this would have a smaller VGS, and a smaller VGS in these voltage regimes means an exponentially smaller current. So, therefore, you would see that it is not advantageous to have series stack larger than 2 transistors in near threshold or subthreshold regimes. So, in low voltage regimes one would not like to have a series stack of larger than 2 transistors, and therefore, we would not prefer to use NAND gate or a NOR gate having more than 2 inputs, otherwise the delays would be quite large. So, now let us discuss the switching currents and mechanism of a 2 input NAND gate. So, let us discuss the turning of 0 to 1 of one of the inputs A and B. The other input is already at VDD. So, it is output discharge that we are discussing. Why we are not discussing output charging? So, for output charging usually one of the inputs A and B would be turning from VDD to 0, the other input would remain at VDD, because the chances of both the inputs simultaneously turning on or off would be relatively smaller. So, therefore, we would mostly be discussing a single input switching. So, turning on of one of the inputs from VDD to 0 would charge the output, but then the charging would be like an inverter. It is just a single transistor which is charging. For example, A is turning from VDD to 0, B is at VDD. This transistor would be off, it would just offer a parasitic capacitance here, and this would be off, this path would be off. So, it would also offer a parasitic capacitance here. Okay. So, therefore, we would be charging the output capacitance through this path. The charging mechanism is like that of an inverter. So, the inverter's delay model and effective current model that we have derived in the previous lecture would be valid with additional parasitic capacitances. So, therefore, we are not much interested in discussing the 1 to 0 transition. To summarize, we are saying that simultaneous switching is not a high priority. So, we do not discuss. Okay. And then we say that the case where one of the inputs, say VB is equal to VDD, VA turns from VDD to 0. So, output charges, okay, to VDD, operation is similar to that of an inverter, and IF2 model of an inverter can be used. Okay. So, now let us discuss the more interesting case of lower transistor of the output. So, here you have a series stack of transistors and the mechanism is different from that of an inverter. Now, we have two cases, that VB is VDD, upper transistor is at VDD, and VA switches from 0 to VDD, and the other case is where VA would be at VDD initially and VB switches from 0 to VDD. Now, both would have different discharging mechanisms and the delays would also be, and effective current values would also come out to be different in both the cases. So, first we are discussing the case where VB is VDD and lower transistor A is switching. Before the switching begins at the input of transistor M1 is at 0, there is a leakage current, so called leakage current flowing through M1, but there is that current must also flow through M2. M2 has a VDS which is drain voltage which is larger than that of M1, the drain voltage, I am not saying drain to source voltage, and M2 has a gate voltage which is again VDD, which is larger than M1. So, whatever be the value of Vx, it would be smaller than VDD because Vout is at VDD, Vx would be smaller than VDD, and therefore, VGS of M1, M2 would be larger than VGS of M1 because M1 would have a VGS 0. So, you are discussing this part where the input is still at 0. So, this is the input, the orange one. So, it has M2 has a larger VGS than M1 and therefore, M1 must have a larger VDS compared to that of M2. because the currents are equal in both of them. This has a larger VGS, so this should have a larger VDS compared to M2. So, VDS when M1 is large, its DIBL factor would be large, and therefore, you will have a, due to the DIBL factor, the current of M1 would match the current of M2. So, we find as expected that when input is 0, we find this blue triangles, this is the node X voltage. Node X voltage is quite close to that of V out. In nominal voltage operation, super threshold voltage operation, you would find that there is a VTH drop. So, node X would have this scenario, node X would have VDD minus VTH. So, node X would have a voltage VDD minus VTH. Here it is not so, because this M2 is also operating in a subthreshold regime. The value of VDD is close to VTH, and when Vx is larger, you will find that VGS of M2 is in subthreshold regime. So, therefore, we find that V would be quite large and it would be comparable to VDD, though smaller than VDD. So, what is the value of this Vx and why do we require it? Because the input A starts switching from 0 to VDD, it is the initial voltage that it finds for VDS of M1 is this value. So, we call this value Vx naught. So, the initial VDS of M1 would be Vx naught, and that is why we are interested in it. So, what would be our approach? Our approach would be, first we will estimate the value of Vx naught. So, when the input voltage is Vx naught, you would find that M1 starts discharging and M2 also begins to discharge with Vx naught. So, M2 begins to discharge with Vx naught, and therefore, the value of, and then what is the value of Vx when output starts to discharge? That is another point of interest for us. So, the output starts to discharge when the value of Vx, see, output starts to discharge here and output begins to, node X begins to discharge here, but output begins to discharge here, and there we find that there is a current through M2. This is the current through M2, and the current through M2 begins to have an important value, almost a non-zero, which you can call a non-zero value, only when the output starts to discharge, that is here. So, how is this entire mechanism proceeding? So, first M1 node A, the voltage of node A begins to rise. When it starts rising, the current through M1 begins to increase. So, that starts discharging node X. So, once the discharging of node X begins, VGS of M2 begins to increase. Since VGS of M2 begins to increase, you find that at a certain value, the value of current through M2 is sufficient to start discharging the output node. Why there is a certain value of Vx needed? Why does not M2 begin to discharge output immediately after Vx begins to discharge? Immediately after Vx begins to discharge, why the output of this drain of M2 or output node, why does it not start to discharge? That is because there is, as node A is charging high, there is a coupling capacitance, between node A and the output node. Okay. So, this coupling capacitance would result in a charging current, this would result in a current charging the output node. So, for output node to get discharged, the current through M2 must equal this current I, or let us call this IMP. So, the output node to discharge the current through M2. So, when does that happen? That happens at a certain voltage of Vx here. So, that is happening here. So, at this voltage of Vx, you find that the output node begins to discharge. So, it means that there this displacement current is equal to the current through M2 at this point, okay, at this value of Vx, because as Vx reduces, Vgs of M2 increases. So, therefore, current through M2 keeps on increasing as Vx reduces. So, let us summarize this. As Va increases, Cx begins to discharge from Vx equal to Vx naught. Okay. Current through CMP charging output node is IMP equal to CMP dVA by dt. When IM2 is greater than or equal to IMP, output node discharges. Okay. Now, let us derive a value for Vx naught. Then we will derive a value for Vxc, which is the value of Vx here. So, first we derive the value of Vx naught. So, here IB is equal to IA. So, it means exponential I naught exponential VDD, VB is VDD minus Vx naught, this is VGS of VB minus VTHN plus lambda, but this is DIBL factor into V out, which is VDD again, minus Vx naught, which is the source voltage of M2. So, this is VDS of M2 plus body factor gamma into Vx naught, which is the source to body voltage of M1, M2 divided by NVT thermal voltage. So, what are all these? Let us label all this. This is VGS M2, VDS M2, VSB M2. Now, this is equal to IB, which is again I naught exponential. What is the VGS? VG is 0 minus source voltage is again 0. So, which is 0 minus threshold voltage Vn plus DIBL factor plus lambda Vx naught body factor, which is again 0. So, let us again label. This is VGS of M1, source to body of M1. Okay. So, what does this give us? So, when we solve this, this gives us Vx naught is equal to VDD plus lambda VDD by 1 plus 2 lambda plus gamma. So, Vx naught, it is proportional to VDD and the proportionality constant is dependent on device level parameters. So, now let us discuss the further discharge. So, as we had discussed earlier, when Vx begins to discharge, the current through M2 begins to rise and that becomes equal to the because VGS of M2 increases and the current through M2 becomes equal to IMP, and that is when further when Vx reduces, the current through M2 increases and beyond IMP, and that is when the output node V out begins to discharge. So, let us look at this. So, now we further see that we want to understand when this becomes to discharge and also till what time is the current linearly increasing. So, it is this point where V out is 0.8 VDD, as we had discussed in the previous lecture for inverter. From this 0.8 VDD to 0.5 VDD, V out reaches 0.5 VDD, you have almost a constant current, and the reason is the same as that we discussed for the inverter. We will discuss that better again. But what we need to realize here is that there is a linear, almost a linear increase in current from V out, from the point when V out begins to discharge and the point when V out is equal to 0.5 VDD, 0.8 VDD. So, between these two there is almost a linear increase in current. So, if we know this lowest value of current here and that is 0 and this value of current which is IH. So, we would be able to get the average value. So, the lowest value of current we would call it IL and this we call IH and we get the average discharging current between the point when V out begins to discharge and the point when V out is pointed VDD. So, to obtain this that is when it begins to discharge, we write KCL at node out. But what is this point? So, till the point when V out begins to discharge, because of IMP, the overall current at node out actually charges node out. So, V out increases though very slowly till that point. So, it is an overshoot at V out and when the current through M2 becomes larger equal to that of the current through the CMP, it is then that you have dV out by dt being 0. Beyond that current through M2 is now larger, V out begins to discharge. So, till here it charges and from here it discharges. So, here you have dV out by dt equal to 0. So, it is that point which we are now trying to understand. So, let us write the KCL at node out. IMP is equal to IM2 minus DCL dV out by dt. So, now we are discussing a case where dV out by dt is 0. So, this second term does not appear in our case. So, we have IMP which is CMP VDD by TR. So, where we are assuming that VA this is VDD and VA is increasing linearly with as a function VA is equal to VDD T by TR. So, this is equal to I naught IM2 which is I naught exponential VGS of M2 which is VDD minus Vxc. So, we are looking at Vx when output begins to discharge or dV out by dt is 0 plus lambda into VDS of M2 which is output voltage is nearly VDD, V out minus Vx. So, which is Vxc okay, minus Vthn plus body factor into Vsb of M2 which is Vxc again by NVT, Vt is the thermal voltage. So, this can be solved as 1 plus gamma plus lambda into Vxc is equal to VDD into 1 plus lambda minus Vthn plus m minus mVt, let us call it, we have been natural logarithm of Cm by I naught VDD by TR. Now, to get a value of this Cm by I naught VDD by TR, we take an approach which is similar to that which we took for the inverter and we say that we use this observation that dV in by dt when V in is equal to VDD by 2 is equal to dV out by dt is equal to dV out by dt when V out is VDD by 2. Now, using this we would say as in the case of inverter we would say that this is equal to IM2 by CL for V out equal to VDD by 2. That is, it is the current at this point. The current at this point we are already knowing and we call it IH. Okay. So, it is the current at this point. So, what is that current? So, this would be equal to I naught by CL. So, I naught exponential VGS at VDD by 2, V out is VDD by 2. What is the VGS value? VGS is this value This is not VDD in this 65 nanometer PDK, it is 0.95 VDD. So, why is it 0.95 VDD? Again it is not VDD because of one of the reasons is that there is a the input voltage is also pulled down by the output fall through these input output coupling capacitances, and therefore, after the output switching is over you see a slight rise in the VDD as we had discussed when we were discussing inverters. This would change from PDK to PDK and to with the transistor technologies also. So, here it is 0.95 VDD, for FDSY it would be lower, for FinFETs it would be even lower. So, like that. These simulation results are for commercial 65 nanometer PDK. Okay. So, when the output voltage is 50% VDD, this is 0.95 VDD, and also what is the value of source voltage Vx? We observe this to be about 10% of VDD. Now, this is valid across fan out loads, that is because of the input output one to one correspondence, as well as there is also another reason that one to one correspondence is actually accurately valid only for inverters. For NAND gates it is valid, but not accurately valid, it is approximately valid. So, but there is another factor which plays out here. When the input, so at this point the input is now stable, it is at a certain value and the output voltage is falling. Okay. So, therefore, the current through M2 would be because the input is only very slowly rising and output voltage is falling. So, therefore, the current through M2 is almost constant because it is very slowly rising and VDS is falling rapidly. So, current through M2 is quite constant as we are seeing here within this region or near this 50% value of VDD. And what about the current through M1? Current through M1 must also, so the input is now fixed. So, there is the current through M1 must also be almost this constant value. So, VDS of M1 should be constant. So, therefore, Vx would also be almost a constant value, very slow changing value, and it should have a value which is almost constant with change in FO also. So, for 50% VDD value, this Vx should be constant with change of FO also. That is because the current through M2 would be dependent. See, this is almost a constant value now, this is very slowly changing, almost a constant value, and the input voltage, and therefore, VGS of M2 would be almost a constant value, and since VG of M2 would be almost a constant value, and because VG of so VGS of M2 would therefore Vx starts to fall. So, V must fall is falling very slowly and therefore, V out is falling rapidly. So, VGS of M2 is slowly rising and V out of M2 is rapidly falling, current through M2 is almost constant. So, current through M1 must also be almost constant because if X is falling slowly, the current through Cx is also quite small, and all these constant, almost constant currents would lead to an almost constant current through M1. So, V would also be value which is almost a constant, and that value is around 0.1 VDD across different PDKs and for different fan out values. It may change from 0.1 VDD to say 0.08 VDD or 0.12 VDD, but depending on the PDK, but it would be a fixed value for every PDK irrespective of the fan out load when for a balanced stage effort case. That is, the case is that of balanced stage effort. The input and output transitions times are almost equal. So, key points are balanced stage effort, Vx at V out equal to VDD by 2 is nearly equal to 0.1 VDD for all fan out loads. Okay. So, therefore, we would set Vx to be 0.1 VDD for this value of for for 50% value of output voltage. And why do we require that? We require that to substitute for VDD by TR. For VDD by TR, we want to substitute some value which would make our calculations simpler. So, here we make this observation that input and output transition times when their respective node voltages are VDD by 2 are equal. So, that gives us this value, and here we now know what is the value of VGS when the output is VDD by 2. VGS is VDD, input is VDD, input B is VDD, it is minus Vx is 0.1 VDD, this value. This we are saying is 0.1 VDD nearly. Okay. So, this is VGS plus lambda into VDS, which is drain voltage or output voltage is 0.5 VDD minus source voltage is again 0.1 VDD minus Vn plus gamma body factor into 0.1 VDD, which is Vx. Okay. This entire thing divided by NVT. Okay. So, now we use this we substitute this for VDD by TR, because dV in by dt at V when V is equal to VDD by T is VDD by TR. Okay. So, we substitute this for VDD by TR and obtain that Vxc is equal to 0.1 VDD plus 0.6 0.6 lambda VDD plus 0.1 gamma VDD plus MVT divided by 1 plus lambda plus gamma. Now, this has a very small dependence, very weak dependence on load capacitance. Nevertheless, there is a dependence, and rest of the factors are dependent on are actually dependent on device level parameters and VDD. So, with change in VDD, variability in VDD, we can estimate the value of change in Vxc, and with the change in device level parameters, we can again estimate the value of Vxc. Here we have considered that this value is 0.95 VDD. If we take it to be, if we do not take this into consideration and say that it is this is VD itself, then this would come out to be 0.1 VDD. Okay. But if we consider that this value is 0.95 VDD, then this comes out to be 0.05 VDD. We have obtained the value of Vx, and that Vxc is coming out to be 0.05 VDD plus 0.6 VDD into lambda plus 0.1 lambda VDD plus NVT CL by CM divided by plus gamma. Now, for this, what is the value of IL? So, we want to estimate that for this value of Vx naught, what is the value of IL? So, here this is VDD, this is Vxc, this is again 0.95 VDD. Okay. We want to find out the current IM2. This is what discharges the output node. So, we want this current value. So, what is the value of that current? When Vx equal to Vxc. it is IDS of a transistor when its VGS is equal to, or rather we say VG 0.95 VDD, VD drain voltage is nearly VDD, source voltage is 0.1 VDD. Why is it 0.1 VDD? As we have discussed, this IM2 must be matched by a current through M1 also, and if Vx rises, IM2 reduces, but IM1 increases, and therefore, Vx would remain at almost a constant value during the discharge, because as we know that current through M2 is almost a constant, Vx is slowly falling, and Vx cannot fall very fast rapidly, because if Vx falls rapidly, then the current through M2 will rise and current through M1 will fall, because its M1's VDS is reducing. So, that cannot happen. So, therefore, current through M2 and M1 would be almost equal. So, therefore, Vx cannot fall rapidly, Vx would fall slowly, because there is a feedback involved here, and therefore, Vx the source voltage of M2, which is Vx, would remain more or less constant throughout the discharge after Vin reaches near VDD or Va reaches near VDD. Body voltage is again 0.1 VDD, and this we can call as IL. Now, we discuss what happens after the value of Vout is 0.8 VDD. So, what happens between Vout being 0.8 VDD and 0.5 VDD? As we are seeing, the current is almost constant. Why is the current almost constant between these two? Because the value of Va is very slowly rising here, and Vout falls rapidly. So, therefore, you have Vg rising slowly and Vd falling rapidly, as in the case of inverter. So, Vgs of M2 slowly rises, back coupling, capacitive coupling through CMX. So, let us call this CMX and CMP. So, this causes the driver, as in the case of inverter, the driver of input A is affected by this, and therefore, the input rise is quite slow in this regime. So, this is slowly rising, very slowly rising. Okay. So, and VDS of M2 rapidly falls, and this leads to a constant, almost constant IM2. So, this constant IM2 we are calling IH is equal to this constant IM2 at Vout equal to VDD by 2, and that is equal to IDS of an N MOSFET for its Vg being 0.95 volts, 0.95 VDD, Vd drain voltage being 0.5 VDD, Vs source voltage being 0.1 VDD, body voltage being again Vx, which is 0.1 VDD. So, this is the value of IH. So, now we have two values. So, between these two values, it is the current is IH plus IL by 2 discharging current, and here the discharging current is IH. So, this gives us the effective current model for lower transistor switching in a near threshold voltage to input NAND gate. So, in this lecture, we have discussed the mechanism of discharge of a NAND gate output with lower transistor switching, and also derived an effective current model for lower transistor switching of a near threshold voltage NAND gate. Thank you.